Hello, today's topic is deep meteorology. This video performed by Nauruzgali Vaxtotta, Zhubanova Farida, and Amangildi Miriamgul. Supervisor Nadir Ablay. Okay, let's start. This is our content. Deep meter, historical date, types, making a deep meter measurements, methods of deep meter data interpretations. Firstly, what is deep meteorology? Deep meteorology is essentially a multi-arm microresistivity log. There are three or four spring-loaded arms record separate microresistivity tracks, while within this zone the magnetic compass records the orientation of the tool as it is drawn up the hole. A software is used to correlate deviations on the logs and calculate the amount of direction of bedding dip. The solution of the dips depends on averaging scale, could be both small scale and large scale. The second one is historical dates. The first date it is 1942. In this year found the first 3-arm Dipmeter used to continuous recording of spontaneous potentials. The second one is 1943. The 3-arm Dipmeter measurements of spontaneous potentials. And the last one, 1969, a new generation of 4-arm Dipmeters for continuous macrolateral log. The next one is types of deep meteorology. 3-directional measurements of rock anisotropy, 3-directional measurements of spontaneous potentials, 3 or 4-directional measurements of microresistivity, 4 or 6-directional microlateral logs, single or double 4 or 6-directional microconductivity logs, 6-directional microacoustic logs. And the important ones is spontaneous potential Dipmeter, resistivity Dipmeter, 3-arm continuous Dipmeter, 4-arm high resolution Dipmeter. The first one is a speed Dipmeter log and photoclinometer. An instrument that measures simultaneously the amount and direction of the deviation of a borehole of zone designed light to exactly parallel to the axis of the borehole is fitted with a small camera on the axis of graduated glass bowl, in which a steel ball rolls freely and compass is mounted in gimbals. The camera electrically operated from surface and takes the photograph of the ball. The steel of the ball marks the amount of deviation, and the position in relation to the image of compass needle gives the direction of deviation. The anisotropy Dipmeter was supplanted in 1943 by a tool using 3 simultaneous spontaneous potential measurements, oriented in 120 degrees apart around the circumference. The second one, resistivity Dipmeterology. The resistivity Dipmeter used 3 lateral curves instead of the SP curves, mounted on the same rubber arms as were used for the SP version. Accuracy was better in hard rock areas. A sample is shown below. Both SP and resistivity Dipmeters were the only recorded over selected intervals chosen by observation of the other open hole logs. Only short intervals where there is a lot of the curve action as suitable for deep computation. And the last one is 4-arm high resolution Dipmeter. In 1969, a new 4-pad high resolution Dipmeter was introduced. The electrodes had even finer resolution than the microlateral log pads, and the electronics were improved to transmit at a higher rate, and so the well could be logged faster and finer bedding features could be recorded. 4 planes allowed for calculation of 4 different sets of 3-point planes, as well as a 4-point curved surface or best fit flat surface. Program logic could be compare all results and eliminate bad correlations, or grade the result to show how well the different results matched. A special speed button on one pad provided information to the program to compensate for minor speed difference as tool moved up the hole. These variations created scatter in computed results. Next one, making a Dipmeter measurements. As the Dipmeter is brought up the well, the electrodes on each arm in contact with the rock layers If the rock layer is dipping, different arms will contact the layers at different depths. The sequence of contacts between individual arms and each layer is used to compute the dip of the layer. If the layer is horizontal, all arms Dipmeter contact the layer at the same time. The Dipmeter measurements provide information related to formational geology, sedimentology, structural geology, and tectonics. The first one, formational geology. It allows to determine micro-horizons as well as collector and non-collector horizons, direction of geological parameter change, saturation of reservoir horizons with hydrocarbon and hibernation water. Second one, sedimentology. It includes determination of deposits, genesis, environment, geometry of sandy, clay, and some carbonate bodies, type of lamination, direction of parameter change, and the point inclusion, porosity, sand clay content, lithology, and thickness. And the third one, structural geology. It enables the determination of formational or seismic structure, components of rocks which have been changed thermally, calculation of structural dip, angle, and azimuth. And the last one, tectonics. It allows you to determine the post-depositional dip of each complex, type and direction of faults, as well as near fault and fault zones, unconformities, and discontinuous faults, breakouts, and fracture zones. The next one, method of Dipmeter data interpretation. It's the express method, quantitative method, stereographic projection, microgeometric analysis. The first one, express method. The images of particular phenomena and geological process are recognized on vectoral plots. It should be noted that we have to do with the apparent dips at this stage of the interpretation. It allows to identify quickly main structural tectonic features just after their physical measurements. We use the analysis of vectoral plots based on SHIVA procedure. It allows to include Dipmeter measurements in a set of standard physical logs. This method was early applied by Schlumberger. The second one, quantitative method, uses the techniques statistical curvative, residual dip, and synthetic dip deviation analysis, which have been worked out and implemented by Benston and Hurley. This is more analytical method than the previous one and less complicated and labor-consuming than the stereographic projection method. It uses the vectoral, angular, azimuthal plots, transversal and longitudinal dip components, intersection of planes at any azimuth or along the borehole, cylindrical and polar plots, dip versus azimuth plots, and others. And the third one is stereographic projection method. Enables the analysis of deep images in details. The structural phenomena can be presented by means of stereographic nets of different types, which are sometimes called stereographs or polar plots. Stereographic projection is a presentation and geometrical construction which allows to analyze the orientation of tectonic elements in space independently of their geographic position. It is a very precise method, but requires a lot of time and use of digital techniques. It should be employed for the detailed interpretation work. The stereographic projection allows to move various structural elements, lines, planes, while keeping them parallel to each other, so that they touch or intersect the top of corresponding hemisphere, leaving trace on a horizontal plane. This plane contains the north-south axis. The intersection of the lines and planes with the hemisphere can be stereographically projected onto a horizontal plane in relation to the south or north pole of the whole sphere. And the last one, microgeometrical analysis, makes it possible to determine the sedimentary, post-sedimentary, micro and mesostructures, continuous, point, and linear, based on the microlateral log correlation. It allows to plot the interpoint graph, spatial image on the plane, or type of cylindrical plot. The method is rather often employed for analysis of seam beds, microresistivity maps, or borehole well oriented microlateral and oriented indication of microcaliper. In conclusion, we want to say the importance of Dipmeter tools is that it provides more accurate information at the well location and detects structural features either beyond seismic resolution or with low acoustic impedance. These informations are important for optimum well positioning, to maximize hydrocarbon recovery. Identification of these structural features and detection of the orientations are done on the basis of structural dip. Trend analysis, which compares characteristic dip patterns of various geological structures with observed dip patterns and computed dip plot. This technique has been applied to field example where a minor normal drag fault has been identified and this orientation have been determined on the basis of structural dip trend analysis. Thank you for your attention.